we have this opportunity to come together and talk about the stars, as we've done since time immemorial as a species. Tonight we have a really great talk from Brandon Shane. Brandon grew up in New Jersey and went to Rutgers University, New Jersey. He's a master student here at Queens, where he primarily studies magnetic fields, the Boogeyman of astronomy. He works on creating synthetic observations of simulations, which is a huge rabbit hole, of star-forming regions to study how magnetic fields affect star formation. Without further ado, I'll pass you over to Brandon. Thank you.
This is mic check. Any mics in the room? No. All right. So it's my great honor to be the first talk of the academic year, which means for many of you, I get to introduce you to the observatory as a whole, as well as our open houses. So I want to just lay down two quick ground rules. One, please feel free to ask any question that comes to mind. Astronomers love to talk, and we love to talk about our research as well as other people's research. So don't worry, ask what comes to mind, anything you can think of. There's no such thing as a stupid question. And two, the answer is never aliens. You would not believe the amount of alien questions that we get. But anyway, in any case, we're not here to talk about aliens. We're here to talk about the boogeyman of astronomy. So what if I told you that there is an invisible force permeating the entire universe that these papers blame for the mismatch in their results and their expectations? Still going. Even mentioning this force in the wrong context will lead to dread and fear in the hearts of even the most esteemed astrophysicists. So unfortunately, Lauren spoiled it. What is this mysterious force? That's right, it's magnetism. The same force that holds your fridge magnets up is the one destroying astronomical observations across the world. But to understand why, we have to start by first asking the same question the great sages of our time, the insane clown posse, asked. Magnets, how do they work? And so let's start small, let's start basics. So when you have magnets, every magnet has north and south. So these are representations of a simple hard magnet. Magnets have two poles, as I've said. Opposite poles attract, like poles repel. So north attracts south, north and south repels south, and north repels north. What's interesting about magnets is if you break a magnet in half, you don't have two magnets, one being all north and one being all south. You instead have two smaller magnets with both north and south, which, if you think about it, very strange. But okay, fine. Well, why this attraction and repulsion? Why like this? The simple idea is that you have these invisible lines called magnetic field lines, which go from one end of the magnet to the other. Namely, they go from the north side of the magnet, they wrap all the way around, and they point to the south side. When you bring two magnets together of opposing poles, such as in the middle panel here, you sort of create a short stop, or a short path for the magnetic field lines to go north to south. And so the magnets will click together. When you bring light poles together, such as the one all the way on the right, you can't create this short path anymore, and the magnetic field lines will sort of push against each other, causing repulsion. And now the first time you hear this, even me saying this now, it's a little ridiculous, right? Like, I'm up here telling you that there are invisible lines that determine which way these magnets go, sort of arbitrarily. Unfortunately, physics doesn't really care about what we think is ridiculous. And so what you're seeing here are real magnets and tracing out their magnetic field lines. So these black spots here are iron filings that are tracing out the magnetic field lines. So on the leftmost panel, you can see the magnetic field lines going north to south. You can see the merging of the magnetic fields in the center, and then on the far right, you can see them being repelled away from each other. So one thing to note, and something to keep in mind as we go forward, is that when you bring two magnetic fields together, it gets a little messy, right? They can bend on each other, they can warp each other, and it's not a lot of fun. But the question is, fine, where do these magnetic fields come from? And in most materials, well, most materials aren't magnets, right? Your clothing probably isn't magnetic, I would hope. So what happens? Well, your clothing is made out of atoms and molecules, and those atoms and molecules each have their own little magnetic fields. But in most materials, they're lined up randomly. So they all cancel out on average. In a small number of materials, namely iron, these atoms, their magnetic fields can group together in what are called domains. And that's what you're seeing in these pictures here. Now, generally, most of the time in iron, it's these domains, these collection of atoms still have their magnetic fields lined up randomly, so it cancels out. However, what can happen naturally and spontaneously is that these domains will start to take over their neighbors, and they'll all agree on the same magnetic field direction. And this is why you get natural magnets like lodestone. So over time, the domains will start to take over their neighbors, and then their neighbors' neighbors, and then they're all pointing in the same direction. You can, of course, force this to happen if you've already got something that's a magnet. This is why if you take like a paper clip and you take a magnet to it and you rub a magnet against it, it'll be a magnet for a little while. Okay, but that doesn't answer the question, right? Because all I said, it was, where did these come from? It comes from atoms. But to understand why atoms have magnetic fields, you have to accept two facts that will help us going forward. And first, again, the first time you hear them, it's a little ridiculous. Uncomfortable fact number one, magnetic fields will deflect moving charges. And uncomfortable fact number two, moving electrical charges will generate a magnetic field. And to show you what I mean, let's see if we can do this fast. Okay, so I've got here a very expensive setup that definitely took me more than 10 minutes to make. So I've got the finest stainless steel nail the boys in the BVEX lab in Sterling could supply, wrapped around in a wire. And I've got a standard D battery. Okay. Now I do have to tell you at this point, don't do this at home, but it's a good thing I'm not at home. I've only burned myself once. So the idea is that when I connect the ends of this setup here to this battery, the charge will move around the nail in a helical pattern, and it should create a magnetic field, which will deflect this compass. Let's find out, and let's see if I burned myself. Yeah, look at that. Pretty simple. It's getting a little hot, but okay. Have I convinced you yet? Hope so, because it's starting to burn. All right. Let's switch back. Okay, great. Okay, so why did I mention that? Well, that's because we have this idea of an atom where you've got a nucleus in the center and electrons, which are electrically charged, moving around. The electrons are the white surface here, and they move around the outside. It's worth noting at this point, actually, that this is wrong. But the truth of electron motion in their orbitals is both vastly complicated and outside of what we want to talk about. So we're going to slap an Ant-Man Quantumania poster on that and ignore it. Okay, so let's use our simplified model here where electrons are moving around the outside. They are moving around the outside, and additionally, they spin. You'll notice that I did the air quotes there, because in the realm of quantum, words are meaningless, and math is the only thing that matters. Okay, fine. So I was able to see the magnetic fields with the iron filings, but can I see them like in a nicer way, in something that's a little cooler? And in fact, you can. So here are two images. One is the aurora. This picture was taken by Matthew Webster, as a grad student in physics and chemistry at about 30 minutes north of here in Loborough Beach. And two, I hope all of you were able to see the solar eclipse in April. If you were lucky when you saw it, and it wasn't too cloudy, you would have gotten a good glimpse of the corona, which is the white wisp part. Both of these structures are formed the way they are because of magnetic fields. If you're not convinced, take a close look at the way these are. So the aurora and the corona, the white wispy part, they have these thin kind of spindly structures to them. This kind of thing is indicative of a magnetic field, that kind of wispy structure. You're going to see it over and over and over. Okay, but let's stay close to home for now. Why does the aurora? Well, it turns out that the Earth is actually a magnetic field. Most of you know this. I even showed you already with the compass. I had this good idea. However, remember the north pole of the compass points towards the north pole of the Earth. That's kind of weird, right? So remember what I said earlier is that the magnetic field lines point north to south. And as you can see in this diagram here, on the Earth, actually, the magnetic field lines go from Antarctica around to the Arctic. So what we call the North Pole is actually the magnetic South Pole. chew on that for a while. So why does the Earth generate a magnetic field? And to talk about that, we're going to have to delve a little bit into geology. I'm not a geologist, so I'm going to do my best here. But the Earth is basically an onion. Okay. And so there's many layers to this onion, and as you go deeper and deeper, two things happen. The temperature goes up and the pressure goes up. So if you start with the topmost layer, that's the crust, that's where we live in. And if the Earth were the size of an apple, the crust would be about as thick as the skin on the apple. So there's a lot of Earth left. If you go one step lower, you hit the mantle, which isn't too important for what we're going to talk about, but it's responsible for things like continental drift and tectonic motions and earthquakes, those kinds of things. What's important for us, though, are the next two layers, the outer core and the inner core, which are iron. And if you remember, we talked about how iron is very important. It comes up. It's sort of the pinnacle magnetic material. But what's interesting here is that the outer core is hot enough to liquefy this iron. And so you've got this slightly lighter orange color, which is this outer liquid shell. And then inside, you've got a denser material that wants to be liquid, but because it has to support the entire weight of the planet above it, it's actually solid. And so this is where the Earth's magnetic field comes from, because you've got this liquid outer core and this solid inner core spinning in it. And what happens is you get essentially the same thing you got with the electrons moving around the nucleus. You have these iron components moving around. And this is a planet-sized version of my little nail electromagnet. Okay. So you have planetary-sized motions, you get planetary-sized magnetic fields. And so while we're talking about the aurora, have you ever noticed that they only happen in the far north and far south? The reason for this is because, again, remember the magnetic field lines go, well, north to south, but to us it's backwards. And the reason they only happen north to south is because electrical charges coming from the sun will be deflected by the magnetic field. Remember, that's one of our two facts. A magnetic field will deflect moving electrical charges. So electrical charges coming from the sun will be deflected around towards the poles, where they interact with the atmosphere. And so these can only happen in the north and south poles, because that's when the magnetic field lines start to come back down towards the surface. And so the characteristic green color of the aurora is actually the color that nitrogen, which makes up most of our atmosphere, gets. It's exciting. Well, okay, but why does the sun eject electrical material? And it turns out, guess what? The sun itself also has a magnetic field. And so what you're looking at here on the left, this orange picture, is sort of a day-to-day kind of picture of the sun, where you get these big flares. They're called solar flares. And again, you'll start to see the same spindly, wispy structures. Now, remember, the sun is many, many times bigger than the Earth. So each of these structures alone, many, many times bigger than the Earth as well. The yellow sort of GIF here is showing sort of smaller scale versions of this, little flares. And so you can kind of get a better idea of what's going on, where the magnetic field causes material to be ejected from the surface, follows the field line, comes back down somewhere else. The sun is, we usually think of it as a big ball of fire, but it isn't. It's a ball of plasma. And so this seems like a kind of fine distinction, or what really matters. Doesn't really matter, but it does, because it's again, it's a very complicated onion here. When you saw the corona during the eclipse, what you're seeing is sort of the most diffuse thin parts of the sun's atmosphere. And so you're seeing sort of the thinnest part of the atmosphere map out the magnetic field at its edges. And so, I guess I kind of spoiled, but a little bit, but that you get your electrical charges, you get your characteristic green color. And so in this way, magnetic fields start to already show a dichotomy, where it is the magnetic field of the sun which ejects the solar wind at us, the electrical charges at us. But it is also the Earth's magnetic field which defends us. So in this way, magnetic fields represent both a sword and a shield. While we're talking about the Earth's magnetic field, I bet you didn't know that the North Pole moves. So when we first started measuring it in 1831, it was firmly right here in Canada. But since then, it seems to have defected and is heading towards Russia as fast as it can. And that's kind of weird, right? Because the North Pole of a regular bar magnet doesn't. So what's the difference? They're both made of iron, right? But the difference is because inside the Earth, remember, it's a solid ball spinning around around a liquid ball. Excuse me, it's a liquid ball, and then inside is a solid of iron. And so this makes things very complicated. So as you can kind of see in this picture here, this white dotted circle, that's the surface of the Earth. And as you go deeper and deeper, the magnetic field gets messy. And if you think that's messy, it can get a lot worse. As it turns out, that the Earth's magnetic field is not stable at all. So you could have such a mess that you get things like multiple North Poles, multiple South Poles, or as some conspiracy theorists like to point out, you can get entire magnetic field reversals, which have actually happened several times in the geologic record, although it's not the kind of thing that could happen overnight. So again, I wouldn't worry too much about that, but it could happen. And so everything I've said already about North being South, you would flip it again. So a little backwards. But if the Earth's magnetic field can get so complicated, you can only imagine how complicated the sun's magnetic field could get. So let's move away from the sun a little bit, and I want to talk to you a little bit about the Galileo spacecraft. So it's a spacecraft launched in 1989, and its goal was to measure Jupiter, to get everything it can, and to measure things about its moons. However, something very weird happened. The onboard compass, which was used to measure the magnetic field of Jupiter, as it passed Jupiter's moon Europa, was deflected. However, Europa is pretty small as far as these things go, so you would expect it to be geologically dead, meaning you wouldn't expect it to have an iron core and a liquid iron core and have this cool dynamo effect that the Earth has. You would expect it to just kind of be sitting there. So what's happening? And for that, I'm gonna ask for a volunteer actually. So don't panic, you're gonna be okay. But by consenting to volunteer, you're gonna be on camera. So anyone want to do it? Don't be scared, don't be shy, come on in. Here, just you. That involved?
Oh, maybe be the camera.
Okay, thank you, back here. Okay, right there's good. Okay, so I have here a cylinder. It's nothing special. I actually don't even know what it's made of, but it's just a cylinder, no big deal. So what we're gonna do, okay, I want you to hold this up kind of like this, and then with your other hand, you're gonna drop it. And I'm gonna tell you when to drop it, and I'm gonna say when to call it. Okay, let's do it. Drop, call. Anything weird there? No. Let's do it again. Just get a feel for it. Go ahead. Drop, call. Nothing weird, right? But if I instead take this neodymium magnet, which is a little stronger than it looks, just like me, and we drop it, do you expect the same thing to happen? I mean, it's just a different metal, right? Drop. Drop, caught. Okay, so it's dropping slower, that's weird. Now, would you mind for everyone, would you look in there and confirm that there's nothing in? Nope, nothing in. Okay, one more time. Drop. Caught. Okay, thank you very much. Okay, so that's kind of weird, right? So is there a gravitational anomaly? Is there something going wrong? For the sake of people on Zoom, and in case it wasn't clear, I do have some videos to see, but I didn't switch thing. Okay, great. So on the left here, we have the not magnet cylinder. I still don't really know what it is. And the neodymium magnet. So you can see sort of, not a great video admittedly, but it will sort of flash as it crosses the barrier, the copper tube. And the neodymium magnet falls a lot slower than the regular magnet. Now, copper isn't magnetic, but what it is conductive. That seems like a fine distinction to make, but it's an important one. Because when the magnet falls through the copper tube, what happens is that the copper tube does not like the fact that there's a magnetic field passing through it. So what it does is it generates its own magnetic field to counter this motion. The faster the magnet falls, the stronger it creates an opposing magnetic field. This is called Lenz's law. The way the saying goes is nature abhors a change in magnetic flux. Any of you read Griffiths? You remember that one? Okay, I got some laughs out of that. That was good. So when the magnet falls, you're seeing a very delicate balance between the strength of the magnet and gravity. If the magnet were stronger, it would fall slower. If the magnet were weaker, it would fall faster. Because as the magnet begins to accelerate under gravity, it changes its magnetic field across the tube faster. And so the copper tube doesn't like that, makes an opposing magnetic field against it, and then slows down. But if it were to stop, you'd have no opposition anymore, so then it would continue to fall. So it's a perfect balance here. Okay, great. Why am I telling you this? Well, it turns out actually that even though Europa is not geologically active in the way we generally think of that, with an iron core or something, it is likely to have a certain conductive material all over the planet. And so as these measurements of Europa's magnetic field were being taken, the compass on Galileo continued to deflect as it moved around Jupiter. And so what was happening was that Europa wasn't, strictly speaking, generating its own magnetic field, just like copper doesn't generate its own magnetic field. It was being induced as it moved around Jupiter. There's the conductive source of this, between this evidence and some more geological evidence, looks likely to be salt water, which makes Europa probably one of the only sources where there's a giant ocean other than the Earth, and a likely candidate for extraterrestrial life here on Earth.
It is alien.
I hit aliens again. Thank you. Let's get back on track. Well, so fine. But why is magnetism a boogeyman? Right? That seems kind of dramatic. Let's start with the sun. So what you're seeing here is what's called a coronal mass ejection. So this white circle here in the center is the main disk of the sun. And you get the same idea as a solar flare, but much, much larger. And so if that white disk is the sun, imagine how big these big arcs are, actually. And so what happens is that the magnetic field of the sun will sort of wrap in on itself and then very suddenly release, and it'll eject material out towards us, just like the solar wind, but on a much greater scale. And these, remember, are moving electrical charges. And remember, moving electrical charges generate magnetic fields. And when two magnetic fields meet, you get a giant mess. So this is a simulation of the 1859 Carrington event. So this solar storm happened in 1859. And the aurora from this storm alone were so intense that you could see them as far south as New York City. Luckily, this happened in 1859. Had this happened today, the people on Zoom wouldn't be watching. The satellites around the planet would be destroyed. And you'd have blackouts all across the world as transformers struggle to keep up the influx. In 1989, there was a similar event, but much smaller, about 3 times smaller in Quebec. That storm knocked out the power grid for 9 hours and destroyed the hydroelectric grid there. Unfortunately, this kind of thing isn't linear. So 3 times worse does not mean only 27 hours of blackout. If this happened today, you're looking at something like months to years, if not decades of blackout. So if you run out of things to worry about, you'll take it. But the sun isn't all bad, right? The sun gives us rainbows. So if you don't know, just quick, sun shines light at the earth, shockingly no. As that light passes through raindrops in the air, it refracts the light, and they separate into the colors to make it a rainbow. What you might not know is that there's a secret code in that rainbow. If you were to take a magnifying glass to this rainbow, you would see these dark patches in that rainbow. And as it turns out, this is kind of the DNA of the sun. Each of these darker lines corresponds either to an atom or a molecule or some kind of transition. And so these are very important for astronomers because these allow us to unlock the chemical signatures of the sun, of other stars. It's a very powerful tool. And so what we have here, sort of all the way on the right, all of this big one, this is actually the DNA, the fingerprints of the sun itself. And so if you took your time, if you were careful, you did a couple experiments, you suffered through chemistry class, you would be able to figure out exactly the chemical composition of the sun from that, which is pretty impressive. But of course, magnetic fields exist. So I'm going to introduce you to another quantum effect, but I'm going to boil it down to its simplest. The quantum effect is called the Zeeman effect. If you have these spectral lines, remember that their positions are very important. But in the presence of a magnetic field, the spectral lines will split into two more components. And these components separate themselves based on how strong the magnetic field is. Translation, the stronger the magnetic field is, the worse this is. And so at best, you'll spend who knows how long trying to figure out what these two imaginary atoms are if you didn't know what a magnetic field was there. And at worst, maybe you messed up your PhD, right? Again, seems kind of ridiculous, but again, physics doesn't care what we think is ridiculous. So what you're seeing here is a sunspot, which are regions of the sun which are relatively colder, still very hot, but relatively colder than the rest of the sun. And they tend to have an increased magnetic field. And so spectral lines in those regions will split. So on the right panel, you're seeing a real spectral line. I don't think it's showing up very well on this screen here, but maybe I'm just too close. But it's split into three components. All right, let's move away from our solar system a little bit, and let's talk about the interstellar medium. So we tend to think of space as being a great big void with nothing in it, and that's mostly true. But there is actually a small amount of stuff between the stars. This is what we call the interstellar medium. It's a bunch of gas and dust, mostly hydrogen, some other things that some people in the room will tell you about. But the idea is this: stars will form in this interstellar medium as you'll have a gas cloud, which will condense under gravity more or less spherically, and maybe you get some thermal resistance from your ideal gas source. As the gas collapses, it gets hotter, like an internal combustion engine. But ultimately, at the end of the day, you end up with a star. Unfortunately, that's not exactly what seems to happen. And I guess I spoiled the skip the animation there, but we'll get there. In a galaxy the size of the Milky Way, you would expect to be something like a couple hundred solar masses of stars to be formed every year. The actual number is closer to 1. So that means that star formation is about 1% the efficiency you expect. So here's my spoiler for the magnetic field. So why does this happen? We don't really know, but we have some ideas. So if you've got a star forming region, so a gas cloud here, some shameless self-promotion, or I guess shameless self-promotion. So in this snapshot of a simulation of star forming region, or of a giant molecular cloud, you've got a magnetic field pointing in the horizontal direction. And so along the magnetic field in the horizontal direction, you will again see these thin, wispy structures that are indicative of magnetic fields. See it again and again. But perpendicular to it, you'll see these denser regions. So what this means is that the magnetic field will allow collapse along it, but prevent collapse perpendicular to it. So it has a preferential treatment for one direction or the other, rather than the spherical collapse. And that's fine, but we're looking perpendicular to the magnetic field here. If you're looking down the magnetic field, as you flip rotate around, we'll see what happens when we point down the magnetic field. Okay, so we're pointing it down. Sorry, I didn't get it exactly 90 degrees, assuming. When you're looking down the magnetic field, so now the magnetic field is sort of pointing at you, the observer, you don't see any dense regions, you don't see any wispy structures, you only see what look like regular gas forms. So what this means is that if you were measuring the star formation rate in this cloud, you would still see a dampened star formation rate, but you would not see the structural influence of the magnetic field on it. So you'd have no idea what's going on. And of course, there are many, many more nightmares. If you're somebody who's into galaxies, one thing you really want to start a study are called active galactic nuclei, AGN. The simple idea here is that you've got black holes that are at the center of galaxies. They're massive, obviously very massive black holes, and they're creating magnetized material, and that material ends up being ejected from the poles. And these are very interesting because they are so bright that they'll outshine their host galaxies. So if you wanted to study the magnetic properties of these guys, you're gonna have to deal with all the stuff between you and that galaxy. We just talked about how the interstellar medium, the ISM, is magnetized. And so when you have these kinds of magnetizations, you get what's called polarization. So if you wanted to study the polarization of an AGN, hopefully there's no polarization between you and it. Similarly, if you wanted to measure the polarization of the cosmic microwave background, you better contend with the ISM in the way. At the McDonald Institute, cosmic rays are a very big thing. So kind of switching gears a little bit. Cosmic rays come from all sorts of things, I suppose, not a cosmic ray. But they're very important because people want to know where they come from. But cosmic rays are moving electrical charges. And you're going to get sick of me saying it, but remember, magnetic fields deflect moving electrical charges. So if you wanted to know where this cosmic ray came from, you better be sure you know where all the magnetic fields were, because each of them would have deflected your cosmic ray. And none of that is to mention that you have to be able to take these observations with ground-based instrumentation or telescopes. As the guys in DVEX will tell you, that you have to contend with the polarization of your telescope, the magnetic fields of people cooking their food in the microwave at lunch. Right? These are all things you have to consider. And so it's just a giant mess. I mean, where do they even come from? Right? Like, it's just so frustrating. Like, are we just the victims of some celestial extraterrestrial beings who just want to frustrate our grad students and terrify us into submission? Okay, I'm sorry. I'm going back to the aliens. I'm losing it. It's not aliens, remember, it's never aliens. But the shortest, most concise way that I can answer where do these magnetic fields come from is, I don't know. And nobody knows. But when physicists don't know something, they like to come up with lots of ideas. Just ask the dark matter theorists when you're there at the McDonald Institute tonight. Okay, that's the last I would to. So the primary idea is this. So the idea is that the galaxy itself is magnetic. So as the interstellar medium and the stars within it physically move through the galaxy, they are playing with the galactic magnetic field, just like Europa passing through Jupiter's magnetic field. But again, that doesn't answer the question, because where do those magnetic fields? And here we get to a part that might be unsatisfactory. The galaxy is moving through the cosmic background. And as it turns out, the universe itself kind of has its own very, very weak magnetic field. And so the answer is essentially just that it does, right? So at the moment of the Big Bang, moment of creation, whatever you want to call it, it seems like magnetic fields just came along for the ride. And that's unsatisfactory at first, but I can ask you, why do electrical charges exist at all? Why does energy exist? Why does anything exist, right? It just does. And so unfortunately, they just do. Okay, what we know about these magnetic fields, and actually I am contractually obligated to talk about this picture. This is a picture of our galaxy taken by ESA and Planck. So this red line down the middle is the galactic plane where most of the stars are, and what you're seeing is tracing the galactic magnetic. So we know that these exist, we know they're there. Why is it called a boogeyman? Like I said, it seems kind of extreme. And why can't we get rid of it? So this is your warning. So I'm going to jump scare you with some vector calculus. So these are Maxwell's equations for electrodynamics. They are about as close to arcane rings as you're going to see. And they're great. They do lots of things. The issue is, though, they're very good at solving for electrical point charges, like electrons, and solids, like regular magnets. What they're not good at is talking about magnetized fluids, right? And that's mostly what we were talking about. Plasma in the sun, the liquid in the Earth's core, the liquid on Europa, the gas in the interstellar medium. They're not very good at that. So if you wanted to talk about that, we're going to have to invoke a dark part called magnetohydrodynamics. Did you hear that? That was the sound of the hearts of every grad student skipping a beat. Magnetohydrodynamics is one of those words that look kind of terrifying when you first see it, but let's break it down. So magneto means magnet. Okay? That's what we've been talking about. Hydro generally means, water, water-like. In this case, we're meaning fluids, any fluid. And dynamics, as the engineering students will tell you, means movement and motion. And so the word magnetohydrodynamics very simply just means the motions of magnetized fluids, right? Not so scary. Unfortunately, Although the word magnetohydrodynamics looks scary, but is actually is not that scary, the math behind it is scary. Believe it or not, these are the ideal equations, which means this is the simplest they can take on. So what that means for us and for you is that these equations aren't actually solvable by hand in any meaningful way. So if you wanted to make a model or a simulation, you need a computer to do a lot of the grunt work for you. Otherwise, you have to make some assumptions that maybe you're not comfortable with. So yeah, it's a giant mess, but it's a mess that we have to deal with, and it's not at the moment not one we can really clean up, but one we have to deal with. And you'll see that this property of moving electrical charges, right? Hope I've shown you, has shown up again and again and again and again. We started with electrons moving around the atom. Then we jumped to the Earth's core, which remember, iron ball spinning around in the fluid. Up to Europa moving around Jupiter's magnetic field. The moving charges throughout the ISM itself moving throughout the galaxy. The magnetized material moving around black holes and ADN. And of course, the galaxy itself moving through the background. And so when people talk about the beauty of astronomy, it's easy to point to pictures of stars and galaxies and stuff. But to me, this is the beautiful part, where you see the same patterns again and again and again and again. And physics, like poetry, rhymes. Magnetic fields, remember, are complicated. But just as a magnet of any size will have both a north and a south pole, magnetic fields of any scale have a pro and a con. So although we talked about how the ISM will destroy your observations of the background or AGN or something, it's only because of the magnetic field that we're able to measure the star formation rate as accurately as possible. And we've already talked extensively about how the auroras are a representation of both how the sun sort of attacks us and defends us. Unfortunately, I couldn't talk about everything as much as I wanted to. Even in astronomy, I didn't get to mention magnetars, which are magnetized neutron stars, so powerful you can rip the iron out of your blood thousands of kilometers away. Or even outside of astronomy, all the weird things magnets can do, like magnet trains, how powerful the neodymium magnets can actually be, or superconductors, which will defy gravity and move around essentially frictionless, but only if they're very. But I'll be around both here and upstairs if you want to talk about that. But otherwise, I've told you for long enough, so please enjoy the stars. Thank you.